Tonight, we're going to talk about the space between galaxies. Not the galaxies themselves, not the stars inside them, but the gaps, the stretches of almost absolute nothing that separate one island of stars from the next. Out there in those gaps, the rules start to feel different. Distance starts to mean something else entirely. Time stretches, light ages, and the numbers climb until they stop meaning anything at all. By the end of tonight, you'll understand what those distances actually mean, what fills that space, and why the scale of it changes how you see the universe entirely. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with something familiar. Step outside on a clear night far from the city and look up. The stars you see are all inside the Milky Way. Every star you can name, every constellation, every naked eye object in the sky above you exists inside the same galaxy as your own sun. Even the most distant naked eye star is just a neighbor by cosmic standards, maybe a few thousand light years away. Our galaxy is enormous, stretching about 100,000 light years from one edge to the other. And yet, it is almost nothing compared to what lies beyond it. Because the Milky Way doesn't exist alone. It exists inside a universe filled with other galaxies. Each one an island of hundreds of billions of stars, separated from us by gulfs of space so vast that our entire galaxy would be a rounding error in the calculation. Let's start with our nearest galactic neighbor, the Andromeda Galaxy. It sits about 2.5 million light years away. That single number is already staggering, but let it settle in the right way. Light moves at about 186,000 miles per second. In a single second, it crosses a distance that would take you more than 200 years to drive at highway speed without ever stopping. In 1 year, light travels about 5.9 trillion miles. 2.5 million light years is roughly 14.7 quintillion miles. That's 14.7 with 18 zeros behind it. And Andromeda is our neighbor, the closest large galaxy to our own. When you look at it in the night sky, that faint smudge of light near the constellation Andromeda, you are seeing photons that left their source around the time our ancestors first began shaping stone tools in East Africa. The galaxy was already there, already ancient, already burning with hundreds of billions of stars. That light has been traveling through empty space ever since, crossing 2.5 million light years of almost nothing to reach your eye tonight. And here's what makes that remarkable. Space between us and Andromeda isn't empty in the absolute sense, but it is the closest thing to nothing that the universe consistently offers. The region between the Milky Way and Andromeda is called intergalactic space, and it is one of the most desolate environments in all of existence. Inside our own galaxy, the space between stars contains roughly 1 atom per cubic centimeter. That's not much by any standard, but it's practically crowded compared to what lies between galaxies. In the deep space between galactic clusters, the density can drop to less than 1 atom per cubic meter. sometimes far less than that. There are regions where you could travel for millions of miles in any direction and never encounter a single particle. Not a hydrogen atom, not a photon of visible light from any nearby source. Just the ancient faint glow of the cosmic microwave background radiation, a relic from the birth of the universe, spread equally in all directions, filling the void with light so cold and stretched it can no longer be seen by human eyes. The cosmic microwave background has a temperature of about 2.7 degrees above absolute zero. That's barely a whisper above the coldest possible temperature. And it fills all of intergalactic space uniformly. It is the only radiation that genuinely pervades the deepest emptiness of the cosmos with any consistency. Every other radiation, every photon of starlight, every galaxy's glow thins rapidly with distance. But the cosmic microwave background is constant everywhere. It is the afterglow of creation dimmed over 13.8 billion years of expansion to a temperature barely above nothing. This is what 2.5 million light years of intergalactic space actually contains. Almost nothing for almost forever. Now, before we can grasp how large these distances are, we need to understand the structure of the space they describe. Because the universe isn't a random scattering of galaxies. It has an architecture, a shape. And understanding that shape is essential to understanding why intergalactic distances are what they are, and why the gaps between galaxies are not uniform, but instead range from millions of light years to billions of light years, depending on where in the cosmic web you happen to be looking. Before Andromeda, before any of the vast intergalactic distances, there is one number worth keeping in mind as a reference. The Milky Way itself, 100,000 light years across. That is the scale of our home. The distance from the center of the galaxy to its outermost disk. The distance across which roughly 200 to 400 billion stars are spread. When we talk about the gap between the Milky Way and Andromeda being 2.5 million light years, we're talking about a distance 25 times the diameter of our entire galaxy. 25 Milky Ways laid end to end would not quite bridge the gap to our nearest large neighbor. And Andromeda is close. The space between the Milky Way and the Triangulum Galaxy, the third large member of the local group, is about 2.7 million light years. The space between us and the Leo Dwarf Galaxy, one of the outermost known satellites of the Milky Way, is already about 800,000 light years. The full span of the local group from one edge to the other is about 10 million light years. That's 100 local Milky Ways stretched across the full width of our gravitationally bound galactic family. And the local group is one of the smallest units in the cosmic web. It is to the full structure of the universe what a single house is to an entire continent. And this is where the scale truly begins to resist the mind. Because even if you somehow accepted the 10 million light years of the local group as a real and tangible thing, a thing you could hold some vague intuition about, the universe doesn't stop there. The next step outward is the Virgo supercluster. And the step after that is Laniakea. And the step after that is the observable universe. Each step multiplying the previous by a factor that wipes away whatever foothold your intuition had just found. And that shape makes the gaps between galaxies even more profound than a simple distance measurement suggests. Galaxies don't float alone in the dark. They cluster together. Gravity pulls them into groups and groups, into clusters and clusters, into superclusters and superclusters, into structures so large that labeling them with a single word feels almost inadequate. Our own Milky Way belongs to a small collection of galaxies called the local group. The local group contains somewhere around 80 galaxies in total, though most are small dwarf galaxies orbiting the two giants, the Milky Way and Andromeda. The Triangulum Galaxy, also known as Messier 33, is the third largest member. It sits about 3 million light years away. The entire local group spans roughly 10 million light years from one edge to the other. 10 million light years of galaxies, dwarf galaxies, satellite galaxies, streams of stripped stars, and gas bridges, all gravitationally bound together. And then, beyond the edges of the local group, the distance to the next significant galaxy cluster is vastly, incomprehensibly larger. The nearest major cluster to the local group is the Virgo cluster. It sits roughly 50 million light years from us. Between the outer edge of the local group and the Virgo cluster, there is a gap of around 40 million light years. 40 million light years of intergalactic space. If you traveled that distance at the speed of light, you would cover 186,000 miles every single second without stopping, without slowing for 40 million years. The sun would exhaust its hydrogen fuel and expand into a red giant during a journey like that. The solar system would be transformed beyond recognition before you arrived. And that is just the gap between two relatively close structures on a cosmic scale. It barely registers when you consider the full picture of what we're about to discuss. To understand why intergalactic distances are what they are, we need to step back and look at what astronomers call the cosmic web. This is the largest known organized structure in the universe, and it is the reason the space between galaxies takes the specific forms that it does. In the very early universe, fractions of a second after the Big Bang, matter was distributed almost, but not quite uniformly. There were tiny fluctuations in density, regions that were ever so slightly denser than the average, regions that were fractionally more empty. These differences were incredibly small, on the order of 1 part in 100,000. But over hundreds of millions of years, gravity amplified them relentlessly. Dense regions pulled in surrounding matter, becoming denser still. Less dense regions lost matter to their neighbors, becoming emptier. Over billions of years, this process organized all the matter in the universe into something that looks at the largest scales, like a vast, three-dimensional web. Filaments of galaxies stretching for hundreds of millions of light years. Nodes where filaments intersect, forming dense clusters containing hundreds or thousands of galaxies, and between the filaments, enormous empty regions called cosmic voids. This is the large-scale structure of the universe. It means that intergalactic space is not uniform. Some of it is relatively crowded, filled with gas bridges and streams of galaxies moving along filaments toward dense nodes. And some of it is almost perfectly empty. The great voids, where almost nothing exists for hundreds of millions of light years in every direction. It is in the voids where the concept of intergalactic distance becomes truly difficult to hold in your mind. Largest well-studied void in our cosmic neighborhood is called the KBC void, named after the astronomers who documented it in detail, Ryan Keenan, Amy Barger, and Lennox Cowie. The KBC void is roughly 2 billion light years across. Our own local group sits near the edge of this void, not at its center. From the center of the KBC void to the nearest significant galaxy cluster on the other side is about 1 billion light years. 1 billion light years of near total emptiness. And as voids go, the KBC void is not even the largest. It is simply one of the best measured. Astronomers using data from surveys like the Sloan Digital Sky Survey and the 2-micron All-Sky Survey have now mapped the cosmic web across billions of light years. What they find over and over is that the voids dominate. The filaments and walls and clusters of galaxies are spectacular, but they are thin. They are the edges of bubbles, not the bubbles themselves. The voids, the emptiness, make up roughly 80% of the universe's volume. 8 out of every 10 cubic light years of space contains effectively nothing. No galaxies, no star-forming gas, no stellar nurseries, just the faintest whisper of the intergalactic medium. A plasma so thin it would register as a near-perfect vacuum by any laboratory standard on Earth. Now, there are galaxies that do live inside voids. They're called void galaxies, and they are among the loneliest objects in the observable universe. A void galaxy sits in the middle of one of these enormous empty regions, far from any filament, far from any cluster or group. Its nearest galactic neighbor might be 50 million light years away, or 100 million or more. Void galaxies are interesting objects in their own right. Because of their extreme isolation, they don't interact with neighbors, don't merge with other galaxies, and don't get stripped of their gas by gravitational tides. They evolve slowly and quietly, left largely to themselves. Astronomers studying void galaxies have found that they tend to be bluer and more gas-rich than their counterparts in denser regions. They haven't had gas stripped away by ram pressure from intracluster gas. They haven't had their star formation quenched by the environmental pressures common in clusters. In a void galaxy, star formation can continue undisturbed for billions of years, slowly building new stellar generations without the violent interruptions common in more crowded environments. The sky, as seen from a planet inside a void galaxy, would look strikingly different from our own. From Earth, on a clear night, you can just barely see the neighboring Andromeda galaxy with the naked eye. A faint smudge, but there. a presence. From a planet in a void galaxy, the sky beyond your own galaxy's stars would be almost perfectly dark. No fuzzy patches of neighboring galaxies. No distant spirals visible with any naked eye effort. Just your own galaxy, an island in an ocean of nothing, with the next nearest galaxies visible only as the faintest specks through a very powerful telescope. The isolation of that situation is hard to fully convey. We already live in a quiet corner of the cosmic web on the outskirts of a modest local cluster. But void galaxies exist at a level of isolation that puts even our solitude to shame. They are stranded in the deep ocean with no shore visible in any direction. It's worth understanding why the voids are so empty, because it's not simply that no matter happened to end up there. It's that matter actively left. As gravity pulled matter toward the dense filaments over billions of years, it pulled it away from the emptier regions. The voids grew emptier, not because they were always that way, but because the universe's architecture drew material out of them and into the walls and filaments surrounding them. The voids are the holes left behind when the cosmic web was woven, and they have been growing ever since, driven by the expansion of the universe itself. This is the other key fact about intergalactic space that makes it so difficult to genuinely hold in the mind. It isn't static, it is expanding. Space itself, the fabric of the universe, is stretching. And this stretching means that intergalactic distances are not fixed. They are constantly growing. Edwin Hubble demonstrated this in the 1920s. By measuring the light from distant galaxies, he found that almost all of them showed a redshift. Their light had been stretched to longer, redder wavelengths during its journey to us. And the farther the galaxy, the greater the redshift. This was the observational signature of an expanding universe. The galaxies weren't moving through space in the ordinary sense of something hurling itself from one place to another. Space itself was expanding between them, carrying them apart, the way raisins in a rising loaf of bread are carried apart, even though none of them moves through the dough. This expansion has enormous implications for what we even mean when we talk about intergalactic distances. When we say a galaxy is a billion light years away, we mean that its light has been traveling for a billion years to reach us. But during that billion years of travel time, the universe has been expanding. The galaxy that emitted that light a billion years ago is now farther away than it was when the light left. How much farther depends on how fast space has been expanding throughout that interval. Astronomers use different measures of distance for different purposes. As a result, the co-moving distance accounts for expansion, measuring how far an object is in the universe's current configuration. The light travel distance, also called the look-back time, measures simply how long the light has been traveling. For nearby objects, these numbers are similar enough to treat as equal. For distant ones, they diverge dramatically. The most distant galaxies ever detected by telescopes, like the James Webb Space Telescope, are so far away that their light has been traveling for over 13 billion years. But those galaxies are not 13 billion light years away from us today. Because space has expanded during those 13 billion years of travel, those galaxies are now tens of billions of light years away in terms of co-moving distance. Their recession velocity, driven purely by the expansion of space, now exceeds the speed of light. Not because they are moving through space faster than light, which nothing with mass can do, but because the space between us and them is expanding so rapidly that the total distance is growing faster than light can cross it. This means we will never receive another photon from those galaxies beyond what we've already detected. The light they are emitting right now will never reach us. The expansion of space will carry them beyond our cosmic horizon before their light can make the crossing. They exist almost certainly. They burn with billions of stars. Their stars cycle through generations. Perhaps something has arisen there that wonders about the same questions we wonder about. But they are lost to us permanently and irrevocably beyond any possible contact. This cosmic horizon is the edge of the observable universe. The distance to it is about 46.5 billion light years in every direction. The observable universe is therefore about 93 billion light years in diameter, not 13.8 billion, as you might expect from the age of the universe, but much larger because of the expansion that has occurred while light was traveling. And within that sphere of 93 billion light years, astronomers estimate there are roughly 2 trillion galaxies, 2 trillion islands of stars, each separated from the others by intergalactic voids. Most of those galaxies are too far away to ever study in detail, even with the most powerful instruments we could ever build. Not because our telescopes aren't sensitive enough, but because the photons simply won't reach us. The intergalactic distances involved are not just large. They are in many cases uncrossable by any signal, any probe, any contact of any kind. The galaxies beyond our cosmic horizon are not part of any possible future for us. They are gone, separated by an expansion of space that no technology can bridge. Now, all of this raises a question that seems almost too basic, but is actually among the most important in cosmology. What actually fills the space between the galaxies? The answer is the intergalactic medium. This is the name for the thin plasma that fills the space between galaxies. It is overwhelmingly composed of hydrogen and helium, the 2 lightest elements left over from the Big Bang, and never incorporated into stars or galaxies. In its densest forms, near galaxy clusters, the intergalactic medium can reach densities of a few atoms per cubic meter. In the vast cosmic voids, it thins to almost nothing. The intergalactic medium is invisible to optical telescopes. Its density is too low, its temperature too variable. It exists as an extremely diffuse plasma. Atoms stripped of their electrons, too thin to emit any appreciable visible light. But in X-rays, portions of it glow with the heat of gas that has been compressed and shocked by the gravity of galaxy clusters. Around massive clusters like the Virgo cluster and the Coma cluster, X-ray observations reveal vast halos of superheated plasma, tens of millions of degrees, spread across millions of light years of space between the galaxies. This hot gas is called the intracluster medium when it's inside a cluster, and it can contain more mass than all the visible stars in the cluster combined. The intracluster medium glows so powerfully in X-rays that massive clusters are among the brightest X-ray sources in the sky, outshining all the stars within them when observed at those wavelengths. In radio wavelengths, the warm and cool phases of the intergalactic medium can be detected in absorption against bright background sources. And in the ultraviolet, the intergalactic medium reveals itself through the absorption of light from distant quasars. As the light from a quasar makes its billions of years journey toward us, it passes through countless clouds and wisps of intergalactic gas. Each cloud absorbs a narrow slice of that light at specific wavelengths corresponding to the hydrogen it contains. By the time the quasar's light reaches our telescopes, it carries encoded within it a record of every cloud of intergalactic gas it passed through on its journey. Astronomers call this record the Lyman alpha forest, named after the specific ultraviolet wavelength at which neutral hydrogen absorbs light. It is one of the most powerful tools we have for studying the large-scale structure of intergalactic space across cosmic time. Through this technique and others, we now know that the intergalactic medium is not a uniform fog. It is structured, tracing the cosmic web itself. Along the filaments, the gas is denser and warmer, feeding galaxy clusters. In the voids, it is thinner and cooler. And threading through all of it is the signature of dark matter. Invisible but gravitationally dominant, shaping the web that the visible matter follows. Dark matter makes up about 85% of all the matter in the universe. It does not emit light. It does not absorb light. It does not interact with the electromagnetic force at all, but it interacts gravitationally, and that interaction alone is enough to build the entire large-scale structure of the cosmos. The cosmic web is at its foundation a dark matter web. The filaments and walls and voids of visible galaxies trace the underlying structure of dark matter halos and sheets that formed first, pulling ordinary matter in after them. Without dark matter, the cosmic web as we know it would not exist. The galaxies would not have clustered in the patterns we observe. The intergalactic distances would be fundamentally different. The whole architecture of the universe depends on matter we cannot see, cannot touch, and whose fundamental nature remains one of the deepest unsolved problems in all of physics. We know dark matter is there because the universe doesn't work without it. Galaxy rotation curves tell us there is more mass in galaxies than we can account for in visible stars. Gravitational lensing shows us that massive galaxy clusters bend light from objects behind them far more than their visible mass could explain. The cosmic microwave background contains acoustic oscillations, whose exact pattern depends on the ratio of dark matter to ordinary matter. And that pattern is beautifully consistent with a universe that is 85% dark matter. The large-scale distribution of galaxies only makes sense if dark matter dominated the gravitational scaffolding on which ordinary matter assembled. All of these independent lines of evidence point to the same conclusion. Dark matter is real. We simply don't know what it is. Physicists have built extraordinarily sensitive detectors deep underground, trying to catch dark matter particles interacting with ordinary matter. Detectors cooled to fractions of a degree above absolute zero, shielded by miles of rock from cosmic radiation, waiting for the rare collision that would prove dark matter's nature. So far, despite decades of searching, no confirmed direct detection has been made. Dark matter remains known only through its gravitational fingerprints on the universe. And then there is dark energy. If dark matter built the cosmic web, dark energy is slowly pulling it apart. Not destructively, at least not on any time scale visible to us, but by accelerating the expansion of space and making the intergalactic distances grow faster and faster over time. Dark energy was discovered in 1998 when two independent teams of astronomers, both studying Type Ia supernovae as distance markers, found something no one expected. The expansion of the universe was not slowing down as it should if gravity were the only force at play. It was speeding up. Both teams reached the same conclusion independently. The universe is accelerating in its expansion. Something is pushing space apart at an ever-increasing rate. This discovery was so surprising and so important that the scientists who led these teams were awarded the Nobel Prize in Physics in 2011. Dark energy, which makes up about 68% of the total energy content of the universe, is the name we give to whatever is causing this acceleration. We do not know what it is. Simplest mathematical description treats it as a property of space itself, a cosmological constant, an energy density that is the same everywhere and does not dilute as the universe expands. Albert Einstein originally included a cosmological constant in his equations of general relativity in 1917 for entirely different reasons, and later removed it. History rehabilitated his equation. The universe really does seem to have an energy density built into empty space, but understanding why it has the specific value it has and what it physically represents remains an open problem. When physicists try to calculate what the energy density of empty space should be from quantum mechanics, they get a number vastly larger than what we observe. The discrepancy is enormous. It means that something fundamental about the relationship between quantum mechanics and cosmology is not yet understood. What dark energy means for intergalactic distances is straightforward. They are growing, and they are growing faster every year. In the far future, billions of years from now, galaxies that are today within our observable universe will begin to pass beyond our cosmic horizon. Their light will cease to arrive. They will vanish from the observable sky, not because they have been destroyed, but because the expanding universe will have pulled them so far away that no photon they emit can ever cross the growing gulf. Billions of years further still, only the galaxies gravitationally bound to our local group will remain visible. Everything beyond will be gone from any possible observation. The intergalactic distances will have grown so large that the universe will appear to any future inhabitants to consist of just a single island galaxy floating alone in a perfectly dark sky. They will have no way of knowing about the 2 trillion galaxies that existed in our epoch. No light from those galaxies will reach them. No record will exist in any radiation they can observe. The universe will have expanded so far that its own history will be permanently hidden from its future inhabitants. That is what accelerating expansion does to intergalactic distances over the longest time scales. It makes them one-way doors that close slowly but permanently. Now, the distance measurements themselves deserve some attention because measuring intergalactic distances precisely is genuinely difficult work. You cannot stretch a ruler from here to another galaxy. You cannot send a probe and time its arrival. You have to be clever. And the history of how astronomers developed the tools to measure these distances is one of the great stories of science. The framework they use is called the cosmic distance ladder. At the lowest rungs for nearby stars within our own galaxy, the technique is parallax. As the Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant ones. By measuring that shift across the full diameter of Earth's orbit, about 186 million miles, the distance can be calculated from simple geometry. The Gaia spacecraft launched by the European Space Agency in 2013 has measured parallax distances for over 1 billion stars within the Milky Way with extraordinary precision. It has essentially completed the 3-dimensional map of our galaxy's stellar neighborhood, a task astronomers had worked toward for centuries. For distances beyond what parallax can reach, astronomers use standard candles. These are objects whose intrinsic luminosity is known from their physical properties, so that measuring their apparent brightness immediately tells you how far away they must be. Cepheid variable stars are the most important standard candle at intermediate distances. These stars pulsate in brightness with a period directly related to their intrinsic luminosity. The longer the period, the brighter the star. This relationship was discovered by Henrietta Leavitt in 1912 while she was studying photographs of the small Magellanic Cloud. Leavitt was working at the Harvard College Observatory as a human computer, one of many women hired to analyze photographic plates. She noticed that among the Cepheid variables she was cataloging, the ones with longer pulsation periods were systematically brighter. She recognized that if all these stars were at roughly the same distance, the period had to be directly related to the star's intrinsic luminosity. Her insight transformed astronomy. By measuring how long a Cepheid takes to complete one full pulsation cycle, you know how bright it truly is. Comparing that to how bright it appears in the sky lets you calculate the distance precisely. It was this method that Edwin Hubble used in the 1920s to determine that the Andromeda Nebula was a separate galaxy and not a gas cloud within the Milky Way. His measurements placed it at a distance well beyond any plausible boundary of the Milky Way. The universe was not our galaxy. It was something incomprehensibly larger. For even greater distances, type Ia supernovae are the primary tool. These are stellar explosions that occur when a white dwarf star accumulates mass from a companion until it reaches a critical threshold and detonates. Because the threshold is essentially the same physics every time, the peak brightness of these explosions is standardized across all of space and time. Type Ia supernovae are so luminous that they can be detected billions of light years away. By measuring their apparent brightness and comparing it to their known intrinsic brightness, distances out to billions of light years can be calculated with real accuracy. And it was this technique, combined with observations of dozens of distant supernovae, that delivered the 1998 discovery of accelerating expansion, changing cosmology overnight and earning a Nobel Prize. Above these direct distance measurements for the most distant objects, astronomers rely on redshift combined with models of cosmic expansion. As space expands, light traveling through it gets stretched to longer wavelengths. The more it has been stretched, the greater the redshift. A galaxy's redshift can be measured precisely from its spectrum by comparing the wavelengths of known spectral lines to the wavelengths at which they appear in the observed light, and by combining that measured redshift with detailed models of how the universe has expanded over time. Astronomers can calculate how far away the galaxy is today and how far it was when its light was emitted. This is how we know the distance to galaxies billions of light years away, not by direct measurement, but by careful inference grounded in well-tested physics. The James Webb Space Telescope, launched in 2021, has extended these measurements to the very edge of what is observable. It has detected galaxies so distant that their light has been traveling for more than 13 billion years, showing us the universe as it was when it was only a few 100 million years old. The earliest galaxies are small, turbulent, and intensely star-forming. They look nothing like the elegant spirals and giant ellipticals we see nearby. They are the raw material of the universe, the seeds from which all later structure grew. Studying them tells us how the cosmic web assembled itself from the beginning. Every rung of the distance ladder depends on the ones below it. Each step introduces its own uncertainties, but the overall picture is consistent across multiple independent methods. We know the scale of the observable universe to within a few percent. The distances between galaxies are as well measured as anything in all of astronomy. Now, there is another dimension to this story that we haven't yet fully explored. The story of how we came to understand intergalactic distances at all. For most of human history, the universe was believed to be small. The stars were thought to be lights fixed to a sphere just beyond the planets. The entire cosmos was something you could imagine reaching if you climbed high enough. Even when we began to grasp that the stars were distant suns, we had no idea how distant they truly were. In the early 20th century, a debate raged among astronomers that is now called the Great Debate. It concerned whether the spiral nebulae, those hazy spiral-shaped smudges in the night sky, were gas clouds within our own galaxy, or were actually separate galaxies, island universes like the Milky Way, but vastly far away. On April 26, 1920, Harlow Shapley argued for the former, Heber Curtis for the latter. The debate was formal, public, and consequential. Both men presented carefully constructed arguments. Shapley based his case partly on some measurements that turned out to be incorrect. Curtis based his partly on reasoning that turned out to be correct. Neither man fully prevailed that evening, but the question was settled within a few years by Edwin Hubble, who used Cepheid variable stars to measure the distance to the Andromeda Nebula. When the calculation came back, the distance was unmistakably outside the Milky Way. The spiral nebulae were galaxies. The universe was not our galaxy. It was something incomprehensibly larger. That realization was one of the most profound revisions in the history of human understanding. We went from thinking the Milky Way was the universe to knowing it was just one galaxy. But the scale kept growing. Hubble's next discovery, that the galaxies were receding, that the universe was expanding, pushed the scale further still. And each generation of telescopes has revealed more. In 1989, astronomers discovered the CF, a Great Wall, a filament of galaxies about 500 million light-years long. In 2003, the Sloan Great Wall was found stretching about 1.37 billion light-years. In 2014, the Laniakea supercluster was identified, spanning 500 million light-years, and evidence has emerged for the Hercules Corona Borealis Great Wall, which may span up to 10 billion light-years, potentially the largest known structure in the observable universe. Each of these discoveries expanded our picture of what the space between galaxies actually looks like. Not just void and isolation, but vast organized structures built from the gravitational accumulation of matter over billions of years. The cosmic web is not a backdrop. It is a living record of the universe's entire history. The local group is worth spending some time with because it is where we actually live, and because the intergalactic distances within and around it are the most concrete for us. The local group is gravitationally bound. The Milky Way and Andromeda are actually approaching each other. Andromeda is moving toward us at about 250,000 mph relative to our galaxy. In about 4.5 billion years, the two galaxies will begin to interact gravitationally. Their outer halos will start to overlap. Stars will be flung into new orbits. Gas clouds will compress and trigger bursts of star formation. Over the course of roughly 2 billion additional years, the two galaxies will pass through each other, separate, fall back together, and eventually merge into a single larger galaxy. computer simulations of this merger are some of the most elaborate ever run in computational astronomy. They track hundreds of millions of individual star particles, each one representing many real stars over billions of years of simulated time. The simulations consistently show the same basic outcome. The two spiral galaxies are transformed into a single larger elliptical galaxy through a process of multiple passes and gravitational scrambling. The spiral arms are destroyed. The organized rotation of both galaxies is replaced by the more random orbital patterns typical of elliptical systems. Astronomers have already given this future merged galaxy a name, Milka, or sometimes Milkdromda. It will be one of the largest galaxies in our local group, though still not especially large by cosmic standards. The intergalactic distance between Andromeda and the Milky Way, currently 2.5 million light years, will close to nothing, not because space between them is contracting, but because their local gravity dominates over the cosmological expansion within their bound system. The merger of the Milky Way and Andromeda is one of the very few cases where an intergalactic distance is actively shrinking. Everywhere else beyond our gravitationally bound local group, the distances are only growing. The Virgo cluster is moving away from us. The Shapley supercluster is moving away from us. Every galaxy cluster outside our local gravitational neighborhood is receding, carried by the expansion of space. What we see in the sky tonight is in a sense more of the universe than anyone will be able to see in the far future. Future astronomers billions of years from now will have a narrower view. The universe's history will be less accessible to them because the evidence will have been carried away beyond the horizon by dark energy. There's something worth sitting within that we live in a cosmically privileged moment. The universe is old enough to have formed rich, complex structures, but it is not so old that dark energy has stripped away the observable record. The full grandeur of the cosmic web is still visible to anyone with the right tools. Now around the Milky Way, within a few 100,000 light years, orbit a collection of satellite dwarf galaxies. The largest of these are the Large and Small Magellanic Clouds, visible from Earth's southern hemisphere as fuzzy patches of light in the night sky. The Large Magellanic Cloud sits about 160,000 light years away. The Small Magellanic Cloud is about 200,000 light years away. Both are gravitationally bound to the Milky Way and are being slowly distorted and drawn in by our galaxy's tidal forces over hundreds of millions of years. A long ribbon of gas called the Magellanic Stream trails behind them, pulled loose by their interaction with the Milky Way. This stream of gas, stretching nearly halfway around the sky as seen from Earth, is a direct physical record of the gravitational interaction between our galaxy and its satellites. It represents material that was stripped from the Magellanic Clouds and is now being incorporated into the Milky Way's circumgalactic medium. There are also several dozen smaller dwarf galaxies orbiting the Milky Way. The Sagittarius dwarf, the Sculptor dwarf, the Fornax dwarf, and others. Many discovered only in the last 2 decades through careful all-sky surveys. Some of these dwarfs are in the process of being absorbed. The Sagittarius dwarf, located on the far side of the galaxy from us, is being torn apart by the Milky Way's tidal forces. Its stars are being pulled into long streams that wrap around the galaxy, ghostly remnants of a former independent galaxy. The Milky Way has eaten many such galaxies over its history. The stellar streams and shell structures in our galaxy's halo are the remnants of those ancient absorbed companions. And Andromeda has done the same. Its outer regions show extensive shell structures and stellar streams. Both of the local group's giant galaxies have grown partly by consuming their smaller neighbors. Beyond the local group, at about 50 million light years, sits the Virgo cluster. The Virgo cluster is a massive concentration of over 1,300 galaxies. It is dominated by 3 giant elliptical galaxies. Messier 87 is the largest. It has a mass of about 6 trillion times the mass of the Sun. At its center sits a supermassive black hole with a mass of about 6.5 billion solar masses. In April 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow. The black hole they imaged was the one at the center of Messier 87. The Event Horizon Telescope is not a single instrument. It is a network of radio telescopes spread across the Earth from Hawaii to Chile to Antarctica, all working together to function effectively as a single telescope as large as the planet. The resolution they achieved was extraordinary, enough to resolve a feature the size of a golf ball on the surface of the moon if the telescope were observing from Earth. The image showed a dark circular region surrounded by a bright ring of glowing gas, exactly as general relativity predicts. That result, directly imaging a feature of a black hole 60 million light years away, is a testament to what becomes possible when you harness the physics of intergalactic space rather than treating it as an obstacle. The light from that black hole crossed 60 million light years of intergalactic void to reach the telescopes, and the Event Horizon Telescope collaboration was waiting to catch it. Messier 87 also produces a relativistic jet, a beam of electrons and other charged particles accelerated to nearly the speed of light by magnetic fields near the black hole, shoots out from the galaxy's core across thousands of light years of intergalactic space. The jet punches through the surrounding intracluster medium, inflating enormous bubbles of radio-emitting plasma that extend far beyond the visible galaxy. These jets are one of the ways that supermassive black holes influence not just their host galaxy, but the entire cluster environment around them. The heat and turbulence they inject into the intracluster medium prevents the hot gas from cooling and condensing into new stars. It is a feedback mechanism operating across millions of light years, connecting the smallest scales of physics to the largest structures in the universe. The Virgo cluster is the gravitational heart of the Virgo supercluster, which spans about 110 million light years and contains dozens of galaxy groups and smaller clusters, including our own local group. And in 2014, a team led by Brent Tully mapped the motions of thousands of galaxies across a vast region of space and found something remarkable. Galaxies aren't just moving apart with the expansion of the universe. They also have small deviations from pure expansion caused by the gravitational pull of nearby mass concentrations. By mapping where galaxies are being pulled toward, you can trace the boundaries of gravitationally connected structures. What Tully's team found was that the Virgo supercluster, along with several other nearby superclusters, are all part of a single enormous structure. They named it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea spans roughly 500 million light years and contains about 100,000 galaxies. The Milky Way sits on its outer edge. At the center of Laniakea is the Great Attractor, a region of unusually concentrated mass about 200 million light years away. For decades, astronomers knew something massive was pulling on the local group, but the Great Attractor lies behind the zone of avoidance, the part of the sky blocked by the plane of our own galaxy. All the dust and gas in the Milky Way's disk blocks our view of what lies directly behind it in optical light. Only using infrared and radio observations that can penetrate the dust have astronomers been able to map this hidden region. The Great Attractor turns out to be a complex of multiple galaxy clusters centered on the Norma cluster, all gravitationally bound together and drawing in surrounding galaxies at speeds of hundreds of miles per second. And even the Great Attractor isn't the end of the gravitational story. Beyond it, the Shapley supercluster sits about 650 million light years away. It is one of the largest concentrations of matter in the nearby universe, containing over 8,000 galaxies organized into dozens of individual clusters. The Shapley supercluster is tugging on Laniakea, adding its gravitational influence to the complex flow of galaxies across our local region of the cosmos. And beyond the Shapley supercluster, the cosmic web continues. Filament after filament, void after void, cluster after cluster, all the way to the observable horizon at 46.5 billion light years. Let's think carefully now about what travels across that emptiness, because it tells us something important about how we know what we know. Light crosses intergalactic space constantly. Every photon from every distant galaxy that has ever reached a telescope on Earth has made that crossing. But light is not the only thing that crosses intergalactic space. Cosmic rays, high-energy particles accelerated to nearly the speed of light by violent events, arrive at our galaxy from all directions. Some of the highest energy cosmic rays almost certainly originate from outside the Milky Way, produced in the jets of active galactic nuclei or in the shock fronts of galaxy cluster mergers. These particles have traveled billions of light years through the intergalactic medium before arriving here, carrying information about their sources and about the magnetic fields they encountered along the way. Gravitational waves also cross intergalactic space. These ripples in the fabric of spacetime, generated by merging black holes and neutron stars, propagate outward at the speed of light. The gravitational wave detectors, LIGO and Virgo, have now detected dozens of these events, each one a signal that has traveled across hundreds of millions of light years of intergalactic space to reach detectors on Earth. The first confirmed gravitational wave detection announced in February 2016 came from two black holes merging about 1.3 billion light years away. That signal traveled for over 1 billion years through the intergalactic void before arriving and distorting the LIGO detectors by a distance far smaller than the width of an atomic nucleus. That detection was a triumph, and it opened a new way of listening to the universe. Neutrinos flood through intergalactic space in all directions. These nearly massless ghost-like particles interact so weakly with matter that they pass through almost everything. Billions of neutrinos from other galaxies, from the cores of distant stars and the remnants of ancient supernovae, pass through Earth every second. They carry information about their sources, and they cross the intergalactic void with almost no interaction, making them potentially powerful messengers for astronomy in the decades ahead. There is one more category of intergalactic messenger that has only recently come into focus, and it is one of the most powerful probes of the void we have yet discovered. Fast radio bursts. These are extraordinarily brief, extraordinarily energetic pulses of radio waves that last only milliseconds, but release in that instant as much energy as the sun produces in days or weeks. They were first detected in 2007 when astronomer Duncan Lorimer was reviewing archival data from the park's radio telescope in Australia and found a burst of radio waves so intense and so brief that no known phenomenon in the Milky Way could account for it. For years, fast radio bursts remained deeply mysterious. They appeared to come from all directions in the sky. Their signals showed a pattern called dispersion, where lower frequency components of the radio pulse arrive slightly later than higher frequency components. This dispersion happens because the radio waves are traveling through plasma. The denser the plasma, the greater the dispersion, and the dispersion measures of fast radio bursts were enormous, far larger than anything that could be explained by gas within our own galaxy. The dispersion was the fingerprint of intergalactic space. These bursts were crossing billions of light years of the intergalactic medium before arriving at our telescopes. Every electron the radio waves encountered along that journey slowed the lower frequencies very slightly. By measuring exactly how dispersed the signal was when it arrived, astronomers could estimate how much electron-rich plasma the burst had passed through on its journey. And that told them something extraordinary. It told them they were measuring the intergalactic medium directly, not through absorption of quasar spectra, not through X-ray emission from clusters, but through the actual physical effect of billions of light years of diffuse plasma on a brief radio pulse. Fast radio bursts became almost overnight a new tool for weighing the universe. The total number of electrons between us and the source of a fast radio burst is proportional to its dispersion measure. By combining the dispersion measure with a redshift-based distance estimate, astronomers can calculate the average electron density of the intergalactic medium along that particular line of sight. Do this for many fast radio bursts in many different directions, and you can build a map of how the intergalactic medium varies across the sky. You can measure whether some directions through the cosmic web are denser in electrons than others, tracing the filaments and voids in yet another way. The Macquart relation, named after the astronomer Jean-Pierre Macquart, who helped establish it, describes how the average dispersion measure of fast radio bursts increases with distance. It has been used to confirm that about half of all the ordinary matter in the universe resides in the intergalactic medium, in the warm plasma that fills the voids and filaments between galaxies. This was a long-standing puzzle in cosmology. The atoms in stars and galaxies account for only about half of the ordinary matter we expect from Big Bang nucleosynthesis. The rest was called the missing baryons. For decades, astronomers suspected the missing baryons were hidden in warm intergalactic gas, too hot to emit visible light, but too cool and diffuse to show up prominently in X-ray observations. Fast radio bursts confirmed it. The missing baryons were there all along, spread through the intergalactic medium, invisible to optical telescopes, but measurable by the dispersion they imposed on brief flashes of radio waves crossing the void. The source of fast radio bursts themselves remains somewhat uncertain, though the current evidence points strongly toward magnetars, a type of neutron star with extraordinarily powerful magnetic fields. Magnetars can produce catastrophic releases of energy when their magnetic fields undergo sudden rearrangements, and the brief, intense radio pulses of fast radio bursts are consistent with what such events would produce. Some fast radio bursts repeat, producing multiple bursts from the same location over time. This has allowed astronomers to precisely localize the sources and confirm they are located in galaxies billions of light years away. And in 2020, a fast radio burst was detected from within our own galaxy, originating from a known magnetar in the constellation Vulpecula. That detection didn't just confirm the magnetar hypothesis. It proved that the same type of source responsible for cosmological fast radio bursts also exists in the Milky Way. The universe uses the same mechanisms everywhere. The physics is universal, and those same mechanisms operating in galaxies billions of light years away are broadcasting signals across the intergalactic void that we are just beginning to learn how to read. It is a reminder that the void, as empty as it is not silent. It carries radio waves, gravitational waves, cosmic rays, neutrinos, photons of every wavelength, from every direction, from every era of the universe's history. We are bathed in messages from across intergalactic space at every moment. We are only beginning to understand all the languages in which the universe is speaking. Stars can also find their way into intergalactic space. During galaxy mergers, gravitational interactions can accelerate individual stars to speeds high enough to escape the combined gravitational pull of the merging system. These hypervelocity stars drift into the intergalactic void, carrying with them any planets that remain gravitationally bound. These intergalactic stars are extraordinarily rare, but they are out there, isolated suns and possibly isolated worlds, sailing through the dark between galaxies on journeys that will outlast any familiar feature of the current universe. The idea of a planet drifting through intergalactic space is worth staying with for a moment. Such a world would be frozen, receiving no starlight, warmed only by the residual heat of its formation billions of years ago, and perhaps by the decay of radioactive elements in its interior. Its sky would be almost perfectly dark. No sun, no system of sibling planets, no neighbor stars, just the distant galaxies, each one a faint smudge of light, and the absolute cold of intergalactic space. If any form of life ever arose on such a world, its entire understanding of the cosmos would be built without the anchor of a nearby star. It would look out into a sky of only galaxies. Its sense of scale would be different from ours. It would have no solar system to use as a reference point, no planets to watch move against the background of stars. It would begin with galaxies as its frame of reference. In a strange way, that might give it a more accurate intuition for the true scale of things than we have. We built our concept of cosmic distance from the inside out, starting with the small and working toward the large. A civilization on an intergalactic rogue world might begin with the large and work inward if they ever found anything to work inward toward. And thinking about that rogue world brings us back to one of the most important and underappreciated facts about the intergalactic void, just how physically empty it is. Not empty the way a vacuum chamber in a laboratory is empty. Not empty the way the space between planets is empty. Empty in a way that has no real analog in human experience. The intergalactic medium in the voids has a density of perhaps 1 atom per cubic meter, sometimes even less. A cubic meter is roughly the size of a washing machine. 1 atom. In the most extreme voids, scientists estimate the density drops to around 1 atom per 10 cubic meters. An atom about the size of a proton, 1/10,000,000th of a meter across, alone in a volume the size of a large wardrobe. For comparison, the air you are breathing right now contains roughly 2.5 times 10 to the power of 25 molecules per cubic meter. That is 25 million billion molecules in every cubic meter of air. The intergalactic void contains 1. If you compress the entire mass of the observable universe into the volume of the observable universe, you'd get a certain average density. Then imagine that same volume, but strip away every star, every galaxy, every black hole, every cloud of gas anywhere near a filament or cluster. What remains in the deepest voids is not merely thin. It is as close to absolute nothing as anything in the physical universe gets. And yet that near nothing extends across 2 billion light years in the KBC void alone. 2 billion light years of space, containing on average almost nothing. If you somehow built a spacecraft and set out to cross intergalactic space, here is what the journey would look like. You would leave the Milky Way, and for the first 200,000 light years or so, you would still be within its halo. Globular clusters would drift past in the darkness. The occasional halo star would appear and recede. Then you would enter the intergalactic medium, real intergalactic space, and the emptiness would be unlike anything within the galaxy. You would travel millions of light years and encounter nothing. Not a star, not a gas cloud dense enough to be visible, not a molecule. The void would be absolute to any human sense. Instruments would detect the sparse plasma of the intergalactic medium, the odd hydrogen atom drifting by, the cosmic microwave background radiation arriving equally from all directions at a temperature of 2.7 degrees above absolute zero. But nothing you could see, hear, or feel. Your nearest stellar neighbor in any direction would be light years beyond the galaxies at the voids, edge themselves millions of light years away. The feeling of scale in that crossing, the intellectual recognition that you are in a region of the universe where the nearest star is so far it would take the entire age of the solar system to reach at the speed of light, cannot be prepared for from within a galaxy. We have no experience that teaches this scale. Our intuitions were built inside the Milky Way, inside a neighborhood of stars where the nearest sun is just 4 light years away. The intergalactic void is several 100,000 times emptier of stars than the interstellar medium within our galaxy. And the intergalactic medium itself is billions of times less dense than the interstellar medium. We are insulated from the true scale of the universe by our galactic address. Living inside a galaxy is, cosmologically speaking, a highly atypical environment. Most of the volume of the universe is void. Most of the volume of the universe contains almost nothing. The galaxies, the stars, the planets, the life, all of it exists in the tiny fraction of space that is not void. It is an almost offensively small fraction of what the universe actually contains by volume. The universe built its most interesting structures in about 20% of its available space. The rest it left as void, as an almost incomprehensible emptiness that serves as context for everything. And it is the scale of that emptiness, not the size of the galaxies within it, that is most resistant to human intuition. We can look at an image of a galaxy and feel something of its scale. 100 billion stars spiraling over 100,000 light years. We can sense the grandeur, even if we can't fully hold the numbers. But the void between galaxies doesn't even give us that. There is nothing to see, nothing to use as a reference point, nothing except the laws of physics, operating in perfect, uninterrupted quiet across distances. Our minds have no tools to grasp. That is the intergalactic distance, not just the number of light years, but the quality of the space those light years describe. Let's also take a moment to consider what measuring intergalactic distances has revealed about the early universe, because this is one of the most powerful connections in all of modern science. The pattern of the cosmic web, the specific sizes of the voids, the spacing of filaments, all of it traces back to density fluctuations that were laid down in the first tiny fraction of a second after the Big Bang. These primordial fluctuations originated in quantum uncertainty at the extreme energies and densities of the early universe during a period of extremely rapid expansion called inflation that is thought to have occurred in the first fraction of a second. Quantum fluctuations were stretched to cosmological scales. They became the seeds of the large-scale structure of the universe. Inflation is one of the most powerful and strange ideas in modern cosmology. The theory proposes that in the first 10 to the power of minus 32 seconds after the Big Bang or thereabouts, the universe expanded by a factor of at least 10 to the power of 26. A region smaller than an atomic nucleus expanded to roughly the size of a grapefruit in an almost instantaneous burst. During that expansion, quantum fluctuations, the inherent fuzziness that governs subatomic scales, were stretched to macroscopic and then cosmological sizes. Regions that would have averaged out if the universe had expanded more slowly were instead frozen in place as slight overdensities and underdensities. These became the seeds. Everything we see in the cosmic web today, every galaxy, every cluster, every void traces its origin to those quantum fluctuations in the first instant of the universe. The specific pattern of overdensities predicted by inflation matches the pattern we observe in the cosmic microwave background. The fact that this match is as precise as it is, that a theory of quantum physics in the first fraction of a second of the universe's existence accurately predicts the arrangement of galaxy clusters billions of light years across today, is one of the most stunning confirmations of the standard cosmological model. It means the intergalactic distances we measure are not accidental. They were set in some deep sense by physics operating at the smallest possible scales at the very beginning. The specific pattern of those fluctuations is imprinted in the cosmic microwave background, the faint afterglow of the Big Bang that we can still detect today. The cosmic microwave background was first detected in 1965 by Arno Penzias and Robert Wilson, two engineers at Bell Telephone Laboratories who were trying to identify the source of excess noise in a radio antenna. They found a uniform radio signal coming from every direction in the sky with a temperature equivalent to about 3 degrees above absolute zero. They couldn't explain it. It took cosmologists to recognize what they had found. It was the heat left over from the early universe, cooled by billions of years of expansion. Over the following decades, Increasingly sensitive instruments measured the cosmic microwave background in finer and finer detail. The Kobe satellite in the 1990s found the first hints of temperature fluctuations across the sky, tiny variations in the temperature of this ancient radiation. The WMAP satellite in the 2000s and the Planck satellite in the 2010s mapped these fluctuations in extraordinary detail. And what those fluctuations show is precisely the pattern of density variations that grew under gravity into the cosmic web we observe today. The same acoustic oscillations that produced the pattern of the cosmic microwave background also left their signature in the distribution of galaxies. The spacing of galaxy clusters today, measured across billions of light years of intergalactic space, carries an imprint of sound waves that propagated through the early universe. These baryon acoustic oscillations, as they are called, show up as a preferred separation scale in the distribution of galaxies. By measuring that scale, astronomers can use galaxy surveys as a cosmic ruler, measuring the expansion history of the universe with precision comparable to type Ia supernovae. All of this, the cosmic microwave background, baryon acoustic oscillations, type Ia supernovae, gravitational lensing, the distribution of galaxy clusters. These are all different ways of reading the same story, the story of how the universe began, how it expanded, how structure formed, and how intergalactic distances came to be what they are. It is a coherent, consistent picture. A universe that began from an extremely hot, dense state, expanded rapidly, developed quantum fluctuations that were amplified by gravity into the cosmic web, and continues to expand today under the influence of dark energy. The intergalactic distances we observe are not mysterious. They are measurements of this history. Each void, each filament, each cluster is a data point in a record that traces back to the very beginning. There is something else the intergalactic void does to light that is easy to overlook. It ages it. Not in the same way that time ages a living thing, but in a physical sense. Light traveling across intergalactic space doesn't arrive the same as when it departed. It arrives redshifted, its wavelengths stretched by the expansion of the very space it was traveling through. A photon that left a distant galaxy as ultraviolet radiation might arrive at our telescopes as infrared. A photon that left as visible light might arrive so stretched that it becomes a radio wave. This isn't a trick of perspective or an artifact of measurement. It is a real physical change in the photon caused by the expansion of the universe over the billions of years, the light spent crossing the void. The redshift is one of the most important observational tools in all of cosmology. It tells us not just how far away a galaxy is, but how fast the universe was expanding at the time its light was emitted. When we plot the redshifts of thousands of galaxies, we are not just mapping their distances, we are mapping the expansion history of the universe itself, charting how space has grown over billions of years. And this is where one of the sharpest outstanding puzzles in modern physics appears. It is called the Hubble tension. The Hubble constant is the number that describes how fast the universe is currently expanding. It has units of velocity per distance, telling you how many additional miles per second of recession speed you get for every additional megaparsec of distance. But here is the problem. When cosmologists measure the Hubble constant using the cosmic microwave background, using the physics of the early universe, they get one number. When astronomers measure it using the cosmic distance ladder, Cepheid variables, type Ia supernovae, nearby galaxies, they get a different number, and the two numbers don't agree. The disagreement is not enormous in absolute terms, but it is larger than the measurement uncertainties on either side. Both teams have checked their work repeatedly. Multiple independent groups have done the measurements using different methods, and the disagreement persists. This matters for intergalactic distances because the Hubble constant sets the scale for everything. If the Hubble constant is slightly different from what we think, then every distance we calculate using redshift is slightly off. The distances between galaxies, the size of the cosmic web, the radius of the observable universe, all of these depend on the Hubble constant. Most likely, the resolution will require some new physics, something in our model of the early universe that is not quite right, something about how dark energy behaves that we haven't understood, or perhaps a new kind of energy or matter that was present in the early universe and has since become irrelevant. Whatever the answer, the Hubble tension is one of the most actively debated questions in cosmology right now. It is a sign that our understanding of the distances between galaxies, as good as it is not yet complete. The intergalactic void hides things. It hides light, absorbs it, redshifts it, scatters it. It hides the history of galaxies in gas clouds that block ultraviolet radiation. It hides the true nature of dark matter and dark energy in gravitational effects that we can measure but not explain. And it hides the answer to one of the deepest questions we can ask. How did the first galaxies form? Because before there were intergalactic distances, before there was a cosmic web, before there were galaxies at all, the universe was uniform, almost perfectly uniform. 380,000 years after the Big Bang, the universe was a hot, dense plasma. Protons and electrons were too energetic to combine into neutral atoms. Light could not travel freely. The universe was opaque, like the interior of a star. Then, as the universe expanded and cooled, protons and electrons recombined. Neutral hydrogen atoms formed. And suddenly, for the first time, light could travel. The universe became transparent. The photons that had been trapped in the plasma were released, flooding out in all directions. Those photons are the cosmic microwave background, the afterglow we still detect today, stretched by billions of years of expansion into the microwave part of the spectrum. After recombination, the universe entered what cosmologists call the Dark Ages. There were no stars, no galaxies, no light sources of any kind except the fading glow of the cosmic microwave background. The universe was filled with hydrogen and helium gas, slightly clumped by the density fluctuations that had been seeded by inflation. Gravity slowly pulled the denser regions together. Over tens of millions of years, the first overdense clouds contracted. The gas within them heated as it compressed. Eventually, in the densest pockets, temperatures and pressures became high enough for nuclear fusion to ignite. The first stars switched on. These first stars were unlike anything that exists today. They are called population III stars, and they were massive. Some may have been hundreds of times the mass of the sun. They burned hot and brief, exhausting their hydrogen fuel in just a few million years before collapsing and exploding as supernovae. But even that brief existence was transformative. They were the first sources of light in the universe, the first fusion reactors, the first factories for heavy elements beyond hydrogen and helium. The heavy elements they scattered into space in their deaths seeded the next generation of stars, and eventually the planets and life. The universe was not the same after those first stars lit up. The photons they produced were energetic enough to ionize the neutral hydrogen in the gas around them. This was the beginning of cosmic reionization, the process by which the universe's neutral hydrogen was gradually stripped of its electrons again by the ultraviolet radiation of the first stars and galaxies. Reionization is one of the major transitions in the universe's history. It lasted from roughly 100 million years after the Big Bang to about 1 billion years after. During this period, the first galaxies assembled. The intergalactic medium was transformed from a neutral fog to an ionized plasma, and the structure of the cosmic web began to emerge. The James Webb Space Telescope is the first instrument powerful enough to study individual galaxies from this era in meaningful detail. What it has found has surprised cosmologists. Galaxies in the first billion years of the universe appear more massive, more structured, and more evolved than models predicted. They look in some cases as if they formed too quickly, as if galaxy formation in the early universe was more efficient than our theories account for. This doesn't overturn the standard model of cosmology, but it suggests that there are details of galaxy formation, the processes by which gas collapses into stars and stars organize into galaxies, that we do not yet fully understand. The early universe is closer to us in some ways than it seems. The physics is the same. Gravity, nuclear fusion, electromagnetism, the same forces that govern our solar system governed the first collapsing gas clouds 12 billion years ago. But the conditions were different. The density was higher. The chemical composition was simpler. The universe was younger and smaller, and the structures that formed from those conditions seeded everything that came after, including the specific arrangement of galaxies and voids we see around us today. When we measure intergalactic distances, we are in a very real sense measuring the outcome of those first billion years. The voids exist where the early universe was least dense. The filaments and clusters exist where it was most dense. The pattern was set long before any of the galaxies within it had formed. And nowhere is this connection between between the early universe and the present more visible than in the objects called quasars. Quasars are the most luminous, persistent sources of light in the universe. They are the extremely bright cores of distant galaxies, powered by supermassive black holes, consuming gas at extraordinary rates. At their peak, a quasar can outshine its entire host galaxy by a factor of 100 or 1,000. A single black hole consuming matter, generating more light than hundreds of billions of stars. The energy comes from the conversion of gravitational potential energy into radiation. As gas falls toward the black hole, it forms an accretion disk. The friction and magnetic forces within that disk heat the gas to extreme temperatures. The gas glows, producing radiation across the entire electromagnetic spectrum, from radio waves to X-rays. Powerful jets of material are launched perpendicular to the disk, shooting out at nearly the speed of light. Quasars were discovered in the 1960s. At first, they appeared as point-like radio sources in the sky, looking superficially like stars, but having extremely unusual spectra. When astronomers measured their redshifts, they found them to be at extraordinary distances. Some of the first quasars identified were billions of light years away, their light having crossed vast intergalactic distances to reach us. The fact that quasars are bright enough to be visible from billions of light years away makes them invaluable probes of the intergalactic medium. Their light passes through countless clouds of gas on its way to us. Each cloud leaves its signature in the quasar spectrum. The Lyman alpha forest, that record of hydrogen absorption we discussed earlier, was first identified and studied in the spectra of quasars. Every bright quasar is in effect a lighthouse, illuminating a column of the intergalactic medium stretching from the quasar to our telescopes. We can read that column like a barcode. Quasars are also concentrated in the early universe. The most powerful quasars were most common roughly 10 to 12 billion years ago, when the universe was much younger, and the supermassive black holes driving them were consuming material at their peak rates. Today, those same black holes have consumed most of the available gas. They have quieted. The quasar era is largely over. The black holes still exist, lurking at the centers of galaxies. Sagittarius A, the supermassive black hole at the center of our own galaxy, was probably a quasar in the distant past. Today, it is almost entirely dormant, occasionally consuming small amounts of gas, but a tiny shadow of the luminous engines that blazed in the early universe. The quasars of the early universe represent a time when the intergalactic distances we now navigate were filled with more activity, more radiation, more hot gas, and more violent events than the relative quiet we see around us today. The universe has calmed. The rate of star formation has been declining for about 10 billion years. The rate of galaxy mergers has been slowing. The universe is aging. Not gone, not dead, but past its most active, most violent youth. The epoch of great quasars, of massive bursts of star formation, of the most dramatic galaxy mergers, is mostly behind us. What remains is a quieter, older cosmos, its structures in place, its galaxies continuing to age and evolve, but at a gentler pace. The intergalactic voids are deeper and emptier now than they were in the early universe. Dark energy has been pushing them wider for billions of years. The filaments are more defined, the clusters more massive, having accreted material over cosmic time. The architecture of the cosmic web is in a real sense more mature now than it has ever been. But it is not finished. Galaxy clusters continue to grow. The Virgo cluster, for example, is still accreting material from the surrounding region. Its gravity is pulling in smaller groups and individual galaxies from the larger Virgo supercluster. In the far future, before dark energy has grown strong enough to halt all accretion, the Virgo cluster will have consumed much of the surrounding galaxy population. The same is happening in other clusters throughout the cosmic web. Gravity is still winning the local battle, even as dark energy wins the global one. Within gravitationally bound clusters, matter continues to fall together. Outside those clusters, the distances continue to grow. The universe is simultaneously being pulled together in islands and pushed apart across the oceans between them. It is worth thinking about what it means that we can observe all of this at all. The light from the most distant galaxies, the James Webb Space Telescope, has detected left its source when the universe was only about 300 million years old. That light has been traveling for over 13 billion years. In that time, it has crossed distances that have themselves grown as the universe expanded around the traveling photons. The photon had no awareness of the journey. It carried no memory of its source. It was simply a wave of electromagnetic energy propagating through space at the only speed it could travel. And at the end of that journey, a telescope drifted in orbit 1,000,000 miles from Earth, caught it, and recorded it. The fact that this is possible, that 13 billion-year-old photons from the edge of the observable universe can be collected and analyzed by instruments built by beings on a small planet around an unremarkable star, is genuinely extraordinary. It requires that the physics governing electromagnetism be constant across cosmic time, that the wavelength of light be a reliable carrier of information about the conditions at its source. That space, despite its expansion, transmits electromagnetic radiation without degrading it. That the universe is in this specific and crucial sense transparent on the largest scales. None of these things were guaranteed. They are features of the universe we happen to inhabit, and they are the reason that we can know anything at all about the distances between galaxies and the structure of the cosmos. The story of intergalactic distance is also, in the end, a story about the nature of observation itself. When we say a galaxy is 2.5 million light years away, we mean that its light has traveled that distance. But we are not seeing the galaxy as it is. We are seeing it as it was. The Andromeda we see tonight is Andromeda 2.5 million years ago. For the most distant galaxies the James Webb Space Telescope observes, We are seeing those galaxies as they were over 13 billion years ago. We are not mapping the universe as it currently is. We are mapping the universe as it was at various points in the past, with the most distant objects representing the most ancient snapshots. The cosmic web we see around us is not a picture of the present. It is a three-dimensional record of cosmic history, with distance serving as a kind of time axis. The nearby universe represents the present. The intermediate distances represent a few billion years ago. The most distant observable galaxies represent the universe's childhood. And the cosmic microwave background at the very edge of our observational reach represents the universe before there were any galaxies at all. In this way, the intergalactic distances between us and remote objects are not just spatial separations. They are temporal ones. When we map the galaxy distribution across billions of light years, we are simultaneously mapping billions of years of cosmic history. The fact that we can do this, that the light from those ancient distant galaxies has survived long enough to be caught by telescopes on Earth, is one of the luckiest and strangest facts about our position in the cosmos. We happen to exist at a time when the universe is old enough to have formed rich structure, but young enough that most of the observable universe is still visible. We happen to be made of atoms that can form brains capable of asking questions about the structure of space. We happen to be on a planet with a clear enough sky and stable enough climate to allow centuries of astronomical observation to accumulate. None of these are certainties. They are circumstances. And from those circumstances emerged the ability to look out at the intergalactic void and understand, at least in outline, what it is. Among all the things that travel across intergalactic space, the most quietly remarkable may be the information itself. Not the photons as physical objects, but what they carry. A photon from a distant star carries information about the temperature, composition, and motion of that star. A photon from a quasar's accretion disk carries information about the mass of a black hole billions of light years away. The pattern of absorption in a quasar's spectrum carries information about every cloud of intergalactic gas along the line of sight. The cosmic microwave background carries information about the state of the universe 380,000 years after the Big Bang. All of this information has been traveling through the intergalactic void for billions of years. All of it arrived intact enough to be read. The intergalactic void is not just an obstacle. It is a transmission medium. The largest, emptiest, most hostile environment imaginable. And yet it carries information across scales we cannot fully conceive, across times that exceed the age of Earth many times over, and delivers that information to the surface of a small planet where curious minds are waiting to receive it. That is the intergalactic void. That is the distance between galaxies. Not just absence, not just emptiness, but space that preserves, that transmits, that connects even across the most incomprehensible separations the universe has to offer. Now, let's come back to the full picture and assemble it clearly. We live in the Milky Way, a spiral galaxy about 100,000 light years across, one of roughly 80 galaxies in the local group, which spans about 10 million light years. The local group sits on the outskirts of the Virgo supercluster, which spans about 110 million light years. The Virgo supercluster is one component of Laniakea, which spans roughly 500 million light years. Laniakea is a single node in the cosmic web, surrounded by other superclusters and separated from them by voids. The KBC void within which our local group is situated is roughly 2 billion light years across. Beyond the voids and filaments surrounding us, the cosmic web continues out to the limits of the observable universe, 46.5 billion light years away. Within that sphere, there are an estimated 2 trillion galaxies. The vast majority of the volume is empty. The cosmic web, with all its spectacular filaments and clusters, occupies roughly 20% of the universe's volume. The remaining 80% is void. This is the true character of intergalactic space, not a uniform sea of thinly scattered galaxies, not an even distribution of matter. A web with nodes and threads occupying a fraction of the total space, and an enormous emptiness filling most of everything. And that observable universe is not the whole universe. It is merely the part from which light has had time to reach us in 13.8 billion years. The actual universe extends beyond that horizon. It may be vastly larger than what we can see. It may be effectively infinite. There is no edge we know of, no wall, no boundary, just more space, more galaxies, more filaments and voids fatting beyond our cosmic horizon into a region that will always be forever beyond our reach. The scale of it is impossible to fully imagine. That has always been true. The distances between galaxies exceeded human comprehension the moment we understood they existed. They didn't become more imaginable as we measured them better. They became more precisely known and more honestly unimaginable. There's a difference between knowing a number and feeling its scale. We can know that Andromeda is 2.5 million light years away. We can write the number, calculate what it implies, measure it with instruments. But the felt reality of 2.5 million light years of near total emptiness, the genuine experiential weight of what that distance means, that remains genuinely beyond what human cognition accommodates. And perhaps the honest response to that is not to pretend otherwise, not to reach for an analogy that almost works, but doesn't quite, but to sit with the fact that the universe is larger than our minds were built to hold, and that this is true and real and worth knowing. There is another aspect of intergalactic distance that rarely gets the attention it deserves. The fact that galaxies come in so many different forms, and that where a galaxy sits in the cosmic web has a profound influence on what kind of galaxy it becomes. The environment of intergalactic space is not neutral. It shapes the galaxies within it. Galaxies in the dense cores of clusters experience an environment radically different from galaxies sitting in relative isolation in the outskirts of the cosmic web. The hot gas filling the intracluster medium exerts pressure on a galaxy moving through the cluster. As a spiral galaxy falls into a dense cluster for the first time, the ram pressure of the intracluster medium can strip the galaxy's own gas out from between its stars. This process is called ram pressure stripping. It is violent and rapid on cosmic timescales. A spiral galaxy entering a cluster can lose most of its cold star-forming gas within a few 100 million years. Without gas, it can no longer form new stars. The existing stellar population continues to age. The young blue stars burn out first. The galaxy reddens as its population shifts toward older, dimmer, cooler stars. Eventually, the spiral structure fades. The galaxy transforms into an elliptical or lenticular shape. The spirals we see in isolated environments are the same basic objects as many of the red ellipticals we see in dense clusters. The difference is environment. The difference is where in the cosmic web the galaxy happened to fall. A galaxy that formed in a quiet filament far from any cluster retained its gas, continued forming stars, maintained its spiral structure over billions of years. A galaxy that fell into a dense cluster had that same gas stripped away and became something different. Intergalactic distance is not just a separator. It is a context. It determines what kind of gravitational environment a galaxy lives in, what interactions it experiences, how long it has access to the gas it needs to continue growing. This is why the most isolated galaxies, those sitting in the deepest voids, are often still actively forming stars. They have never fallen into a cluster. They have never had their gas stripped. They are, in a sense, the youngest of the old. They formed early in the universe's history, but they have continued developing ever since, protected from the violent transformation that cluster membership brings. The voids are not just empty. They are for the galaxies within them a kind of refuge, a place where the pace of change is slower, where galaxies can evolve quietly over billions of years without the dramatic interruptions of mergers or the slow strangulation of ram pressure stripping. The cosmic web's voids contain galaxies that are in some ways more pristine than the galaxies that live in denser environments. The galaxies within voids are also physically smaller on average. Without the constant accretion of material from dense filaments, without major mergers to supply new material and trigger star formation, void galaxies grow more slowly. They contain fewer stars. They are fainter. Many are only detectable with modern instruments sensitive enough to find the faintest surface brightnesses. Some of the smallest and most isolated galaxies in the observable universe sit in the deepest voids. They are the survivors, the galaxies that happen to form in regions the cosmic web passed by. Now, some of the most spectacular structures in the universe are found not in the voids, but at the intersections, the places where multiple filaments of the cosmic web meet. These nodes are the sites of the most massive galaxy clusters. The Coma cluster sits about 320 million light years away. It contains over 1,000 galaxies, most of them ellipticals and lenticulars, already transformed by their dense environment. The total mass of the Coma cluster is enormous, several 100 trillion times the mass of the Sun. Most of that mass is dark matter, about 80%. The rest is split between the hot intracluster gas and the visible stars in the galaxies themselves. The Coma cluster was one of the first places where the evidence for dark matter was recognized. In the 1930s, the Swiss astronomer Fritz Zwicky studied the velocities of galaxies within the Coma cluster and found they were moving far too fast. The visible mass of the cluster was nowhere near enough to provide the gravitational force needed to keep the galaxies bound. They should have flown apart long ago. Zwicky concluded that there must be enormous amounts of matter we couldn't see holding the cluster together gravitationally. He called it dark matter. His conclusion was largely ignored for decades. It took the work of Vera Rubin in the 1970s, measuring the rotation curves of individual spiral galaxies, to provide the more compelling observational evidence that eventually convinced the astronomical community. But Zwicky was right. The Coma cluster and every other galaxy cluster is embedded in an enormous dark matter halo. The dark matter halo is what holds the cluster together. It was the dark matter that collapsed first, forming the gravitational well into which gas and eventually galaxies fell. If you could somehow make dark matter visible, the cosmic web would look even more spectacular than it already does. The dark matter filaments extend far beyond the visible galaxy filaments. The dark matter halos around clusters are vastly larger than the bright galaxies at their centers. The true scale of the cosmic web is the dark matter scale. What we see in the visible light of stars and galaxies is just the lit surface of a much deeper, much larger structure. There is also an intermediate scale that doesn't get discussed as often as it should. The scale of galaxy groups. Most galaxies in the universe don't live in massive clusters. They live in groups, smaller, quieter collections of anywhere from a few to a few dozen galaxies, typically spanning a few million light years. The local group is a galaxy group. The Sculptor group, about 11 million light years away, is another. Groups are the most common environment for galaxies in the universe, and within groups, the dynamics are different from clusters. The velocities are lower. The gas filling the space between galaxies is cooler and less dense. Ram pressure stripping is less severe. Galaxy mergers within groups tend to be slower, more gradual. The dwarf galaxies orbiting the Milky Way and Andromeda are being absorbed. Yes, but the process unfolds over billions of years. The tidal forces are real, but not catastrophic. The group environment is a slow motion version of the cluster environment, and the intergalactic distances within a group, a few 100,000 to a few million light years between major members, are the kind of distances where our galaxy's future will unfold. The Milky Way and Andromeda will not encounter a dense cluster. They will merge with each other, consuming the smaller members of the local group over the next several billion years. And then they will exist in relative isolation as the rest of the universe expands away. The intergalactic distances beyond our local group will continue to grow. The Virgo cluster will recede from us, and the merged milk-drummed galaxy will eventually float in a universe that appears from any telescope within it to contain just a single island of stars. The future of intergalactic distance is isolation. Dark energy ensures that. Not immediately, and not on any time scale meaningful to human civilization, but over the longest scales the universe permits, the distances between galaxy groups will grow beyond any possible communication. The universe will fracture, not violently, not suddenly, but slowly and irrevocably, into isolated islands of matter that can never again exchange photons with one another. And yet, even in that ultimate isolation, something of the universe's history will persist. The atoms that formed in the first stars, scattered by supernovae, accumulated into galaxies, incorporated into planets, and eventually into living things. Those atoms don't go anywhere. They are part of whatever structures form over the immense time scales of the future. The universe forgets nothing. It only spreads it out. We should also spend a moment on what is actively being learned right now, because the story of intergalactic space is not complete. The Euclid Space Telescope, launched in 2023, is mapping the shape and distribution of billions of galaxies across billions of light years. Its primary goals are to understand dark energy and dark matter by measuring the geometry of the cosmic web with extraordinary precision. The Rubin Observatory's legacy survey of space and time, coming online in the mid-2020s, will image the entire accessible southern sky, repeatedly building the largest ever catalog of galaxies and other cosmic objects. The Square Kilometer Array, a massive radio telescope facility being built in South Africa and Australia, will eventually detect the hydrogen gas tracing the cosmic web across vast distances and in unprecedented detail. These are not small updates to existing knowledge. They are transformative expansions. Each of these instruments will see the intergalactic universe in ways we have never seen it before. Each will answer some of our current questions and almost certainly raise new ones. The future of our understanding of intergalactic distances is not a matter of refining existing measurements. It is a matter of genuinely new discoveries. Things we don't currently know that we don't know. That is the nature of science at the frontier. We come back finally to that smudge of light in the night sky. Andromeda 2.5 million light years away. Our nearest large neighbor across the intergalactic void. When you look at it, you are seeing the accumulated light of about 1 trillion stars. Stars that exist right now, burning and fusing and aging in their own galactic neighborhood, unaware of their distant neighbor, gazing back at them. The light reaching your eye tonight left Andromeda 2.5 million years ago, and it crossed in that time a gulf of space so empty that the entire contents of that crossing would fit inside a thimble, 1 atom per cubic meter, sometimes less. 2.5 million light years of near total nothing. And yet here it is. The light made it. The information survived the crossing. The photons that left Andromeda's stars 2.5 million years ago have arrived. That is the strange miracle at the heart of intergalactic distance. The space is incomprehensibly large. It is almost perfectly empty. It is expanding, driven by a force we cannot explain. It is filled with a web of structure whose origin traces back to quantum fluctuations in the first instant of the universe. And yet across all of that, light still travels. Information still crosses the void. The universe still communicates with itself, photon by photon, across distances our brains were never built to hold. We can measure those distances. We can map the cosmic web. We can trace the history of structure formation across billions of years of cosmic time. We cannot travel there. We cannot send anything there in any meaningful time frame, but we can know it. And knowing it in a universe this vast, in galaxies this isolated, across voids this empty, and distances this enormous, is perhaps the most remarkable thing in the observable cosmos. So the next time you look up at Andromeda, or at the faint glow of the Virgo cluster in a dark enough sky, remember what you are looking across. 2.5 million light years, or 50 million, or billions. Remember that the space between those galaxies is not simply a gap. It is a structure, a record, a consequence of the universe's beginning and the laws that govern its evolution. Remember that the light reaching you has crossed that void without help, driven only by the physics of electromagnetism for longer than our species has existed. And remember that we live here in this small gravitationally bound island of the local group, surrounded by an ocean of intergalactic space that stretches in every direction to a horizon 46.5 billion light years away. Beyond that horizon more, always more, an expansion that does not stop, a universe that does not end at the edge of what we can see. We are small. Our galaxy is small. Our local group is small. But we are the part of the universe that looked out into the void and began to understand it. That looked at the distances between galaxies and tried earnestly and persistently to comprehend what those distances mean. And in that effort, in that act of measuring and calculating and wondering, something genuinely rare is happening in this corner of the cosmos. A universe that knows something about itself. And on a night when the sky is clear and the Milky Way arches overhead and Andromeda hangs just visible to the naked eye, that is not nothing. It is in its way everything.